Good morning. Welcome to this session in the Red Room, and thank you for coming here, escaping the APT definition madness in the other room. This talk is definitely proving to be much more, and looking for the paper is going to be much more interesting than the other thing in that room, who can define these APTs anyway. So we have Alexander Chailytko from Checkpoint, who's going to talk about interesting integration between those two tools that we very commonly use, IDA and Olly DBG. Alexander.
Thank you. So, hello and welcome to the presentation about our tool meant for malware researchers and reverse engineers called Labeless. First of all, let me introduce one of my team members who has done most of the programming work for the project. It's Aliaksandr Trafimchuk. He's working as malware researcher in my team, but unfortunately he's not on the stage today. And my name is Alexander Chailytko. I'm a team leader for malware research team in Checkpoint. A little bit about myself. I've started to learn things about malware and hacking and all this stuff at the age of 14. And my first serious project was at the age of 17. So basically, it's more than 10 years of experience for me in the sphere of reverse engineering. When we started developing Labeless, we haven't realized that it will come up like that. Even at the stage of proof of concept, my whole team started to use that tool in our day-to-day work, and it's improved our productivity by a significant amount. So now we want to present this tool to you. And by the way, it's available as open source and on our Bitbucket, and we will be posting the link in the end of our presentation. So let's start. Here are the problems that we've been facing in our day-to-day work. The first problem is that we cannot synchronize labels on the fly between IDA and Olly. The second problem is that we were using an inconvenient and manual way, basically import reconstructor tool, to fix imports and in our dumps. And finally, the third problem is that if we needed some sort of data to be found, processed, and sent back from IDA to the debugger, we were writing a script for Olly, executing it there, then exporting the result of the file, then writing another script for IDA to work on that exported data set. So you've got a point, it's like not seamless interaction. And it took much time, and that's it. Now it's all changed with the help of Labeless. So let's take a look at the main features of Labeless. They will all be discussed in more details later. The first feature is label synchronization, and it's image-based independent. The second one is dumping code directly from Olly, and we call this feature IDA dump. Automatic on-the-fly imports fixing while dumping. Remote Olly Python scripts execution, and IDA Olly scripting synergy. In order to better understand all further material, let's start from a quick overview of the architecture of Labeless. Labeless is a two-component system. One part of the system is running on the IDA side and the other on the Olly side. They share the same core interface called PX core. Basically, all the communications are done through it. Since it's the most significant part of the system, let's take a look at it in more details. PX core provides like RPC server-client communication functionality, and that's how the IDA and Olly are able to hear each other. And if something needs to be done, RPC request will be issued. Then it will trigger an underlying module, which is responsible for the type of requests. Right now we have like 3 underlying modules. It's IDA dump module, it's label synchronization module, and Python scripts execution and interaction module. So what's under the hood of Labeless? We're using IDA API in Python for IDA side plugin module, Python for Olly side plugin module. It's basically switch-generated wrappers around Olly DBG API, and protobuf-based communication protocol for all kind of RPC server-client interactions. Now let's start to take a look at the label synchronization feature. For example, we've opened some executable in IDA and produced meaningful names for all the functions. They are all saved in IDB. And now we start a debugger and have no information here. So we just have dummy function addresses instead of names. And of course, it makes debugging process an unpleasant experience. It's like debugging without symbols, basically. So what are the existing solutions for that? The first one, we can use a map file, but there are limitations. For example, it requires a lot of steps to be done manually. We need to export labels from IDA to files and transfer that file to the virtual machine, then manually select that file from the menu and find what to import, and finally apply it. It takes too much time. Also, automatic updating of labels is not supported, so you need to perform aforementioned steps every time you update something in IDA. And rebasing is not supported, so it's if the model that you're working on will be mapped to a different image base, you'll be in trouble and forced into even more work. Another possible solution is to apply labels manually by hand, but it's time-consuming and it's getting worse when the IDB grows and it's error-prone. So to address these issues, Labeless was invented, and it allows seamless synchronization of labels, which include function names, comments, global variable syncing with demangling. We can synchronize all this information on demand by clicking Sync Now button in IDA, and also automatically on any rename event. So every time you change a label or function name or something else in IDB, this data will be automatically propagated to the debugger. And finally, we support image-based independent synchronization. We'll talk about that in a minute. Here's how the executable looks like in debugger if you have no labels. Even if we have a perfect IDB, we're still blind in that environment. And now we use Labeless. Now it looks much better. So what's base-independent synchronization? It means that even if the executable will be relocated on the next run to a different image base, for example, due to malware executable dynamically allocates memory in a different region, we will still be able to synchronize labels like nothing happened. Here's an example. On the left, we have a module mapped at the image base that you can see on the screen. We have the IDB that contains that model also mapped at this address. And on the right, we have the same module but mapped at a different image base. What can we do? We can fill all labels by hand. It takes too much time and leads to obvious errors. And we can also try to rebase the model in IDA itself. But usually it leads to problems with jumps, calls, offsets, and all this kind of stuff. And finally, we can force binary to allocate memory and address that we need. But this requires a lot of additional tracing and controlling of the executable. Or we can just use Labeless. Despite 3 completely different image bases, we're still able to sync labels and other information. Now to the next, and from my point of view, the most powerful feature of Labeless, IDA dump. IDA dump is a feature that allows you to dump any memory region of the executable directly to IDB without using any third-party tools, while automatically fixing imports on the fly. There are use cases when using IDA dump can be really beneficial. For example, the debug process has injected model which doesn't bring the models list. A heap spray was performed. No valid P header. Corrupted import table. Analyzed model contains stolen bytes. Or while following multiple injections. Here's how the main view of the IDA dump looks like. We can select required regions of memory that needs to be dumped or provide them manually. There are three modes of operation of ID dump. The first one is wipe and import. It will wipe your current IDB and dump selected regions to it. The second is add segment. It will preserve your current IDB and add a selected region to it. And the third one is override segment. You can think of it like an update. How does it all work? Basically, ID dump performs safe memory read, avoiding page guard tricks. Also, it performs exported functions and API scan in external modules and fixes these functions references in target IDB. So it's basically imports fixing capability. P-header analysis is being performed, so if it's valid, it helps ID to decide where the data is and where the code is. And finally, it performs post-processing analysis of dumped code. Here's how post-processing analysis is performed. We have calls and jumps like that, and the code references by such calls and jumps will not be disassembled by IDA in the dump. We're tracking such situations, fixing them, and forcing to disassemble. Now let's talk about how ID dump can be useful when following multiple injections. First of all, we'll discuss a case how to solve the problem without ID dump. Here's our malware, and it injects itself into process number 1. So we can dump that region using ordinary tools like load-p, restore-p header, and fix imports using import reconstructor tool. And finally, we transfer the resulting dump from virtual machine and load it into the IDA. Then malware performs another inject into the second process. We are performing all of our mentioned actions again while loading the resulting dump in a separate IDA instance and separate IDB as well. Malware can perform a lot of injections like that. We will end up with a lot of separate IDBs without any connections between them. It's like crazy. And here is the solution that ID dump provides. Once again, here's our malware. It injects itself into the first process. We're dumping that directly to the IDB with automatic fixing of imports. And then it injects into the second process. We're dumping once again using add segment mode of operation. That dump region will be added to the same IDB. So here are the advantages of using ID dump. All valuable information is located in one IDB file. We call it single research case, one IDB. No need to handle multiple IDA instances and look for correlation with other databases. The same external section for jump and calls operation is basically a legitimate fixed imports table. And also sections relations are preserved. We also have some disadvantages at the moment. For example, mapping regions of memory with addresses that is already used. However, we have a solution for that. We can use segments in IDA to address this issue. We just need to implement that. Next, imports fixing functionality. Here's how we usually make jumps and calls human readable in dumped memory without using ID dump. We'll use some dumping tool and then apply import reconstructor-like tool to that dump to restore imports. And basically, it's a lot of numbers, a lot of data, and a lot of room for errors. So there are even more disadvantages. For example, you need to perform manual search of imports table in already running binary. You also need to manually calculate relevant offsets and addresses. Import table may reside in multiple sections. It's time-consuming and error-prone. So here's our solution to that problem. We have an IDB with dumped memory regions, but they have an unresolved imports table. So Labeless is sending a request to enumerate all loaded modules in the target process. Then it will gather all exported functions from these modules alongside with their addresses. This data will be transferred to IDA and stored in the Labeless internal structure. Next, we find all unresolved calls, jumps, etc. in our IDB. We take that address and check if we have it in external structure. If yes, we return a label for that. Create an external segment and place an appropriate import record here and fix it in the code to point to that record. Basically, we're restoring imports tables on the fly. So we go from this to this. Advantages are obvious. For example, no need to perform error-prone tasks such as searching for sections with imports or manually calculate offsets and addresses. The next advantage is automatic fixing of functions located in external modules. It's quicker than any existing solution, and it saves precious researchers' time. And it can be performed on the fly while dumping the process, resulting into the seamless experience. And the last feature of Labeless, IDA scripting interaction. Here's the main ID view of it. On the left side, you can see the code that will be executed in IDA, and on the right side, the code that will be executed in Olly. It has syntax highlighting, different color schemes, error reporting, and a lot of other stuff. These scripts can share data between them. For example, we can produce a dictionary in IDA, place it into an external variable, and propagate it over same data on the Olly side. It's a complete scripts interaction. Here's how it works internally. We're feeding IDA and Olly Python scripts provided by the user to Labeless scripting engine, which is the part of PX core. Then we execute an IDA Python script and fill in external variable. It will be passed alongside with Olly Python script to Olly DBG. Finally, it will be executed in Olly. External variable will be used as needed, so we can pass any data here. And the conclusion. Labeless is automatic tool for on-the-fly label synchronization between IDA and Olly that supports model rebasing. It's automatic tool for on-the-fly imports fixing that is faster than any existing tool. It's convenient tool for IDA Olly scripting synergy. And easy to use memory dumping tool. So, of course, there are some areas of improvement. We want to add a WinDBG support. It will virtually allow you to dump the code directly from kernel while remove debugging. And we want to add an x64 architecture support. And the best of all, Labeless is available as open source. You can find it on Bitbucket, and you can see the link on the slide. Also, I have a demo of how our tool works. I don't know if it can be seen. Yeah. So basically, we have a region in Olly where the malware resides. So here's the function. And basically, we want this in the IDA. And we can easily dump it using IDA dump. We're just testing the connection to the virtual machine. It's talking to the RPC server. The connection is OK, so we select wipe all and import. So we'll create a new IDB, basically, with the region that we need from Olly. So we just select this region, click OK. It is transferring data between Olly and IDA right now, so you can see live how it's propagating data. And here is the fixed imports. So you just click on any region, select any region, and it will automatically restore imports and everything. Also, of course, it will grab the strings and all other stuff. So it's pretty easy. So here's the strings, all here, just with one click. Also, if the malware is performing like multiple injections, we'll be showing it later. You can select another region that you want to dump, and it will be dumped into this database. And we'll add the imports to the same external region, so it will be all in one database. You'll be able to see it later. So we've run a malware for some time, and it's injected itself to different addresses. A7000 and A2000. So it's the new addresses that needs to be dumped. We just select Labeless, ID dump, keep existing and import. So preserving the database, current database, and selecting the new regions that need to be dumped. Click OK. And as you can see, there are functions that are dumping directly into IDA from Olly, with also all the imports restored. So that's basically it. Do you have any questions?
Thank you very much, Alexander. This was really great presentation, so let us thank Alexander with a round of applause. Okay, do we have any questions from the audience? Anybody? So, okay, so I'll have one question. My question is whether you guys contacted the IDA guys about this, because it seems like it should also almost be like an integral part, considering the fact they also have integration with some other debuggers, although not as powerful as this.
Basically, when we were working on the project, we found some bugs in IDA, so we contacted Ilfaq Gulfanov to fix those bugs, and they're building custom builds for us, basically. And we will be pushing that into the 2016 plugins contest. So we will see. They will notice us anyway.
Okay, so eventually it may become a part, who knows?
Yeah, why not?
Okay, that's great. Anybody else? More questions? No? Then let us thank Alexander once again, and thank you for the great presentation. It's time for break.